So this is the assignment that it's due tomorrow. So make sure that you complete it by tomorrow, because next week we will move on and we will do something completely different. Well, not completely different, but we will move on and we will be doing other things. We can always improve this file. Okay, so this file is an ongoing file. So here we have this for walls. Then you have to include something about roofs and floors. But I think, Tim, you asked me on Monday, well, no, not on Monday, last week, if there's a place in which we can find all the thermal conductivities together so that we don't have to look up on the internet, okay, I want the thermal conductivity of this, let's look it up. And so, yes, there's a place. And I want to show you that there's a wonderful website, which is the engineering toolbox. Okay, so this engineering toolbox, it's for engineers, but well, it's quite, it's not appealing, to be honest, but we have all the information that we need about engineers, units, a lot of things. Okay, so it's too advanced. Here we have HVAC, hydraulics, thermodynamics. What we are doing now, basically, it's the thermodynamics. Okay, but what I want to find is if this engineering toolbox, we have thermal conductivity. And we do have thermal conductivities for solids, liquids, and gases, thermal conductivities. So you click here and you have this wonderful table with first, you see that here we have, by default, we have watts meter Kelvin, okay? And if you click here, we have these units in blue. The units are BTU, feet, hour, Fahrenheit. So what can we do here? Because units are important. The units that we are using in our Excel file are BTU, inch, Fahrenheit, feet square, hour. But the units we have here are either this, the international system units, or in blue, we have these ones. We have the BTU, feet, hour, Fahrenheit. Okay, so none of these units are the units we're looking for. So in this website, we have watts divided by meter Kelvin, and we have BTU, hour, Fahrenheit, feet, and finally we have BTU, hour, Fahrenheit, feet square, inch. Okay, so we have to move from these units easily. It's quite complicated. Of course, we can't learn by heart all these materials with the thermal conductivity. So we need tables. And sometimes it's useful having a table in which we have all the materials together with different units, because we don't know. We will do this with Revit, by the way. So with Revit, we can calculate these kind of things just immediately. So we don't have to operate, or we don't have to write down anything, or we don't need the Excel file. So in Revit, if you specify the layers of your material, of your walls, you will get the thermal resistance of that wall immediately, or the roof. But Revit, I know that Revit uses these units, BTU, hour, feet, Fahrenheit, feet. In other software, you will find those units. So, and in the Excel file that we are preparing, we are using these units. So we need to access the 3 units, and sometimes if you are working for an international company, they will be using the international units. Okay, so we have the same concept, the thermal conductivity, but if we, especially from international to imperial units, there's a huge mistake. Okay, so if we mistake international units for imperial units, our calculations will be totally wrong. So we have to be careful because we know the concept, but now we have the issue with the units. So what would I do now? Okay, let me try. If I copy this, Control C, and I'm going to open another tab here. Okay, so by clicking here, this plus sign, you are in the same file, but with two different sheets. What if I paste it? Okay, so we can do that. Okay, let's do it. I'm going to copy from this engineering toolbox. I'm going to copy all the materials. We got all the materials up to here. Okay, Control C, and then on this file, I click Control V, and I paste it. So here, let's deal with this unit, because here the first unit that I have on this website is watts meter Kelvin. Okay, so this is the black one, or the black font. It's a watt divided by meter Kelvin. Then the blue one is BTU, hour, Fahrenheit, feet. So I can change the format if I select the blue font. Okay, so now we have the black font is this unit, the blue font is this unit. But we need something else, we need something different. By the way, we can get rid of these two columns because we don't need this. Okay, but in this column, I would like to have another different unit. And the units here are BTU, inch, divided by hour, Fahrenheit, and feet square, square feet. And I can use a different color font here. Okay, so I have three colors and three different units. So how can I turn this into the other units? Well, we have to find out. So we need a converter from BTU hour Fahrenheit feet to BTU inch hour Fahrenheit feet square. So we can always Google these converters. Online. Okay, so we have this online unit converter for thermal conductivity. Okay, so that's quite good because here we have the units. By default, we have international units, but we want this BTU hour foot Fahrenheit. And then we need to convert this in BTU inch hour square foot Fahrenheit, this one. So it's 12. I have to multiply by 12. Okay, so what do? I use this column here equals this times 12. There you go. And now we can either copy. Okay, so every time I copy this, where we have blue figures, example here, it doesn't work because for wool, for wood wool, we have a range between 0.057 to 0.08. So it doesn't work here. So what do? I don't know. I can either dismiss this material, or I can make a decision here like an average. So this is from 0.05 to 0.08. So let's type here 0.07 and something in the middle, an average. And now we have a value here. Okay, so if we keep doing this, where all the blue values are, then I keep getting thermal conductivities in the right units again here. But now we have to understand if we need these materials. because here we have too many materials, and we don't want all these materials. So do we want xenon, the gas? It's not a construction material, so delete it. Do we know wool? Wool. Well, I don't know. Wood, we might need this. This is wood across the grain, yellow pine timber. Well, this is a specific wood. It's fine having all these, but we need uranium or tungsten. All these we can delete. Okay, and so on and so forth. You see that we have thousands of materials. By default, we can delete all these that come in blue with a link, because there's a link to, if we click here, so there's a link on to this material. So by default, we can delete all these lines that are using, because they are not construction materials. Okay, so if you right click, delete all the cells, you delete all the cells at the same time, or you can go one by one. But if you press Control and you keep selecting all these elements, we can keep deleting them just by clicking on delete. Okay, so I would, yeah.
So just to refresh myself, when we go to the engineering toolbox, where do we go from there to find that chart?
You have well, in the engineering toolbox,
Yeah.
I think moving with the engineering toolbox is quite difficult. So I typed engineering toolbox thermal down and then here I have the first link. I have is solid, liquid, and gases thermal conductivities. And then you get this. Okay. But I mean, that's good, because in that part of this file, you have the materials. Well, the materials, you have the walls that you are creating. And here we have a new material. You can go to heat number 2. And here you can see, okay, what's the thermal conductivity of oak? So it's a 1.17. Okay, and you can deal with this. So you're working with your own Excel file. There is not a tool available on the internet for free that you can find in 1 minute in which you have everything you need. You have to work on your own. Okay, so this is what you are doing. You are working on your own Excel file that you are going to use for this course. And so the goal is not just that you know how to calculate the R value, is that you are generating your own tool to calculate R values for different walls. Then you will use other tools. Okay, so I don't think that you will be using this when you are 50 years old, or maybe you will, I don't know. But for this course, this is all what we need, and we don't have a tool available online that we can use. So you have to prepare it yourself. And then you can, it doesn't mean that it has to be ended today. So when we are using this, do we need some of the, okay, so I didn't delete these two, so you can keep working on that. So it doesn't mean that it has to be finalized today or tomorrow. So you will be using this file for a long time, this course. So keep adding things. But the most important thing is that we have 3 units here. We have 3 columns, the material, then we have the international units, imperial units, and second imperial units. And the units that we have to use are the red ones. Okay, so if we are working with this Excel file, you have to use this column. But do not delete this column, because it will be useful. Okay, maybe not today, but in the future, if you're working with Revit, or if you're working with other software, probably you will need to go and get the international unit value for wood, or oak, or something else. So having this in the same file, it will help you a lot. Okay, so we're working with this, and if you want to look it like more professional, you can name this. It's not heat 1, heat 2. You can rename this like walls, and then this is the sheet number 2. It's the thermal conductivity of materials. Okay, so now here, if someone opens this file, they know how to use it. So you have an interface that it's good enough, and by moving here, and then there's another thing that I will teach you how to do. Would it be great if we just type here Greek, and we have the thermal conductivity of the Greeks in the cell? That would be great. I'll show you how to do it, but not today. Okay, so imagine that here we have different names. So if we start typing here Greek, whatever, we get the thermal conductivity in that cell. By the way, what happens? Well, I don't know why, but it has ordered all these the other way around. You have wool the first and acetals the last. I mean, do you have this order? It's upside down, so it starts with the W and ends with A, or is the other way around?
No, mine starts with A.
Okay, I don't know what I did, but we can always, if I click here and oof. Okay, so here we have a format, conditional formatting. Well, I don't know, because it's not the same layout that I have in my computer, but there's a way to reorder this in the alphabetical order, not in the other way around. I think it's sort and filter. Yes, here. Sort and filter. Okay, so I want to sort A to Z. So I do this, and I want to expand the selection, because if I change this column, I want to change other columns as well. So I select sort, and all them are going to be the same size. Okay, I can't do it because the merge cells have to be the same size. Okay, we can fix it. Anyway, now it goes from W to A. Doesn't matter if your file goes from A to W, that would be even better. That I don't mind. Anyway, because I wanted to start with the A, and with the A, well, there at the beginning, we have some materials that we are not using. We are not using acetals, we're not using acetone or acetylene or acrylic or this. The first material should be the air. Okay, so I can get rid of all these materials. Delete. And we have air, atmosphere or air when the elevation is 10,000 meters. Probably if we were on a plane, that would be useful, but we are not on a plane, we're in buildings on the earth surface, so we delete it. Alcohol, we are not using alcohol in buildings, at least not in the walls or in the so this aluminum, can get rid of it. And then we have aluminum brass, aluminum oxide, antimony, this. We don't need apples. Argon, well, argon is different because we can use argon in glasses.
Yeah, Windows.
In Windows, not in glasses, in Windows. So especially when we have a triple glazing, we have glass, then we have air chambers, and we call it air because we want to simplify things. But sometimes we fill those chambers with something that is not air. So the most common gas to fill air chambers is this argon. And look at the thermal conductivity of the argon. So we are looking at the blue figures. It's 0.009. In the air, which is the other option, it's 0.015. Okay, so this is much better because it's lower. The lower thermal conductivity, it's always better. Okay, so in glazing, in windows, we use argon to fill the chamber. So we call it an air chamber, but sometimes we fill it with argon, which is much better than air in terms of thermal conductivity. Okay, so we can use argon. For example, all these asbestos, now it's a cancerous material. I would delete it, because nobody's using those kind of materials anymore. Asphalt, we do use asphalt. Sometimes in flat roofs, when we want to waterproof that roof, we use something that is a kind of asphalt. So I would use it. A balsa wood is the wood that we use to create models. We don't use this as a construction material, the balsa wood. I will delete it. Beef. Benzene, no, and all these. Okay, so I'm not going to use all those. Bitumen. Bitumen, again, it's another material that we use for waterproofing, we can use this in basement walls, on the roof, but we can use bitumen. Furnace, I would do this, and the boiler either. And we're not using this. Okay, that's enough for today. But remember, every day that you open this file, you can delete a few of the materials that we're not going to use, and that's fine. Okay, so we have a lot of materials, more materials than we need. Remember that we have to, we can do this, we can drag this, and we do it, we will do it everything at once. The problem is that for the black cells, we don't want to do it. We want to do it only on the blue cells. Okay, so we will have to delete this. So we can do it all at once and then delete, or we can just copy and paste this on the blue cells. Okay, so little by little, you can build this. It will take a while, but you don't have to do it. You don't have to prepare all the table the same day. So if you are working with assignments or exercises, okay, what's the concrete block? Do we have a concrete block here? It should be somewhere cellulose concrete. Okay, so we have concrete blocks. And we have concrete lightweight, concrete dense. Well, again, and we have a range here from 0.578 to 1.04. So again, we have to make decisions here. But remember that when you find something like this, you can get rid of it. And as you are, you need materials, you can fix all the problems that we have in this table. Okay, but little by little, you will be building up your own table with thermal conductivities with different materials and different units. Okay, so go ahead and save it and make sure that you work with this. So this is the assignment that you have to complete by tomorrow. So remember that you have to look at this, all the materials, you have to use the Excel file, and then copy and paste your Excel file here on this assignment, save it, and submit it on Canvas again. And what's next? So that's the meaning of this first slide. We have to decide what the thermal envelope is. And we are losing heat. Assuming that we're in winter, we have 20 Fahrenheit outside, we have 70 Fahrenheit inside. So we are losing heat through the roof, we're losing heat through the glass, we're losing heat through the wall and through the floor. Common sense, where do we have to place the thickest thermal insulation? On the roof, second on the wall, third on the floor. So if we have to protect this against the cold weather, the thinnest thermal insulation should be on the floor. The thickest thermal insulation should be on the roof. But we have allies, especially in winter. Yes, we have a lot of heat losses, but we have heat gains too, because if we have sun and the windows are well oriented, we have a lot of solar energy entering through the windows. Okay, so at the end, we have a balance between the energy that we are losing and the energy that we are gaining. So we have to try to create even a positive balance. If we get more energy that we are losing, we don't need a heating system. If we have if we lose more energy that we are getting, then we need a heating system to make the balance zero. Okay, but even in winter, we might in a very cold winter, like in New Hampshire, we might have spaces inside the thermal envelope in which we don't need the heating system. And if we can do this, that's the first goal, to save energy and to create zero energy buildings. If we don't need a heating system, even when we have a very cold temperature outside, we're doing things good. And as you can see, the orientation makes a difference, because if we have big openings to the south, there will be a lot of solar energy entering the building. But if we open big openings to the north, we will be using a lot of energy, and there's nothing we can do to compensate that. So that's why if you look at this building, the biggest windows or the curtain walls are on this side, which is the south side. The windows on the north side are smaller than the windows on the south. So this is basic to understand what good architecture is. And it's very basic. You don't have to go to a graduate school in Harvard to understand that. You have to understand this from the very beginning. Orientation matters. And we have to look at the masters. I always recommend my students go to see the Zimmermann house by Frank Lloyd Wright. Okay, it's in Manchester, New Hampshire. So again, you don't have to go too far to understand what good architecture is in this country, in this area of the world. So the Zimmermann house makes the most of the weather. So this is the north elevation. So on the north elevation, we have very small windows, just because we need a little natural light in this area. But in the south elevation, we do have, so everything is made of glass. Okay, so this is the south elevation. We have a long overhang because in summer it's the other way around. In summer we have to protect the house against the solar radiation because it can be too much. But in winter we can make the most of solar radiation in the southern facade, but we have to open minimum windows on the northern facade. And that's it. I mean, looking at this house, I know I can stop here and that's it. Okay, do this. I don't need to say anything else on this course. Look at this house and realize what it works in this area of the world. Northern facade, minimum openings. Southern facade, it's made of glass. And then you need a tilted roof to get rid of water. And this is what a single family house should be in this area of the world. Unfortunately, if you look at residential buildings, they don't look like this. And everybody agrees that it's a great building. If you are there, you like it because it's very charming. You have a fireplace, the materials are quite good. Everything is beautiful, but nobody does it. I know. but this is it. Okay, so if we are studying this, this wouldn't be the right option, because here I have opened a small window to the south and a big window to the north. There might be a reason to do this. Imagine that we have the most spectacular view to the north. And okay, so shall I open a very small window when I have something very beautiful facing north? Okay, if you have this requirement, but you have to know that you're doing something that it's not the most efficient way to address the architectural design of a building. But sometimes we might need to do this. Okay, so I don't think that, oh, I can't open a big windows to the north. Sometimes you will have to, because your client will demand this. What? I have bought this site and I want to see this. Yeah, but it's facing north. You shouldn't do it. Okay, so again, designing buildings, it's about making decisions every time. So this is the first thing we have to understand, and this is the first thing that we have to. So we need to understand basic physics in what happens inside the house. So basically, we lose heat. We are talking about winter. We lose heat through the envelope, through the roof, the walls. We have allies, so the solar radiation. It's something that we have to consider, because in sunny days in winter, we can have enough energy so that we don't need any heating system here. But if we need a heating system, we need a heater, we need a heat source inside. And by moving the air, by heating up the air in one part of the room, then the air is moving. And then we can get, or we can have the same temperature, comfort temperature around the house. Okay, so we need to consider this, the envelope, openings, the heat source, and then how the air moves inside the window, inside the house. Sorry. But again, in these first weeks, we are working with the building envelope, and so let's work with this. And I'm going to use the Excel file with 1, 2, 3, and 4 different things. So let's do it. We have done it before, but I told you that we have to do it again many times. Okay. So here, in this case, we don't have to look up anything. We have the thermal conductivity and we have the width. So let's do it in this Excel file. If my wall only has one layer, basically I only have brick, I have a brick wall without any thermal insulation. I have to keep the exterior and interior air, and I can delete 2 layers. So this is just brick. The thermal conductivity is 5. The width is 4. What is the R value? 1.77. Do you happen to remember what was the acceptable R value according to the standards? 38. Okay, so we are far from 38. Without thermal insulation, you can increase this up to 20 inches, and it's still 4. Well, that's another way to address this question. What is the thickness that we need for a brick wall to get 38 as a thermal resistance? We can do it. But how many inches do we need? Let's say 200. Okay, with 200 inches, we are above 38. Does it make sense? Maybe, I don't know. Oh, without thermal insulation, it's possible. Well, it's not impossible. You can have a 200-inch wall, and you get a good thermal resistance. But it's possible, but it doesn't make sense. So this is the first slide. The second slide, we have more materials. And here we have a fiberboard, which is a thermal insulation, but we only have ½ inch. Okay, so here we need 3 materials. So the first material is brick, then fiberboard, and then plywood. So remember, brick, fiberboard, and plywood. The second layer is the thermal conductivity, 5.38 and 0.8. 5.38 and 0.8 for the plywood. And thickness 4.5 and 1. 4.5 and 1. What's the thermal resistance? 4. We're far from this. Why? Because the fiberboard should be the thickest layer, and it's only ½ inch. What is the thickness of fiberboard that we need to get close to 40? 10. Yeah, we said something like this, 10 inches. 10 inches. 10 inches, it's the other one, the expanded polystyrene. But for the fiberboard, we need at least 15. Okay, so 10, 15 inches. Remember that number, 10 or 15 inches, depending on the thermal insulation that we are using. But using 1 inch, 5 inches, not an option. Okay, so don't even try. Start trying with 10. If it doesn't work, move to 15 because otherwise it won't work. Okay. So here we have this. The next one is this one. Okay, so that's another question that you can have. What's the minimum thickness that we need? If our goal is an R value of 50, what's the minimum thickness of fiberboard? Okay, so using this, 5 inches not enough, 10 inches doesn't work, 15 inches, it's about 40, but we need 50. So let's type 20. Okay, so probably 18 inches would be enough. Yes, 18 is the answer. Okay, so this is another question that I can ask you. I can give you the materials, the thickness, and then you have to calculate the R value. Or I can give you the R value that I want, and then you have to, using these 3 materials, you have to give me the thickness of the thermal insulation that you need. So in this case, the answer would be 18. And the correct answer is 18. It's not 17, because with 17, we are below 50. And with 19, we are above 50, but it's not the minimum thermal insulation. So 18 would be the right answer. Okay. These questions. Here we have 4 materials: brick, concrete block. We have EPS and drywall. I think we did this last time, but we're going to do it again. So I need to insert a new layer. So it's brick. The second is the concrete masonry unit. And then we have the fiberboard. No, the EPS, sorry. EPS and plywood. And here we don't have any values about the thermal conductivity, so I have to look it. Look it up on the internet. So I have 4 inches, 4 inches, 6, and 0.5. So it's 4, 6, and 0.5. Okay. Now, what about the thermal conductivity? I can use the table that I had in that lesson, or now I have thermal conductivities here. So let's go to brick, concrete masonry unit, EPS, and plywood. Let's see if we get all this information from this. First, brick. What kind of bricks we have here? So again, we have different bricks, dense, brickwork, brick insulating, brick fire, brick dense. There are a lot of them. By the way, I need to copy this cell. And then I go back to the brick. And here where we have the blue figures. Okay, so all these bricks. So we have values, the brick insulating. So an insulating brick, it's something that is special. It has been manufactured with the insulating aggregates. So that's why we have a very low thermal conductivity. We have thermal conductivities that range from 4 to 9. In the other table, it was from 5 to 9. So again, I don't mind. You can type 4, 5, or 8. I don't mind. So let's type for the sake of yeah. So if we want to get the worst possible material that we have outside, let's type. No, it's not the worst. Come on, I'm making the same mistake. The worst would be the highest, so it's 9. The worst material in terms of thermal conductivity would be the highest thermal conductivity. So I have to type 9. Okay. Then, do we have concrete masonry units here? Let's find out. So there will be, I want to copy this, and then there will be concrete. We have concrete here, stone. We have concrete, medium. We have concrete, lightweight. Here we have a range. We have concrete, dense. But we don't have concrete masonry units. Okay, so this is something else we can do. If we don't find the material, we can always insert a new layer. And let's use here concrete masonry unit. Okay, so if there is not a material on this table, we can find or we can do our own material. If we are using concrete masonry unit, we have to open the file that we can find on this lesson. This one. And we're going to do it again. We go here and we have the concrete block or concrete masonry units. So remember that we had this thermal resistance, 0.8, and the concrete block is a 4-inch concrete block. So what's the thermal conductivity? It's 4 divided by 0.8. So the thermal conductivity is 4 divided by 0.8. So the thermal conductivity of a concrete masonry unit can be 5. So I can type here 5 because I'm in this column. Okay, so I'm not in the blue. The units are different. I'm in this column. So a concrete masonry unit should be 5. So I'm going to type 5 here for the thermal conductivity. Then EPS. Do I have expanded polystyrene? I think so. Yeah, I have it, but it's under polystyrene. Okay, so here we have polystyrene expanded. Yeah, but I need to turn this so I know that this equals 12 times this cell. Okay, so it's 0.2. I remember that in that table, it was around. Here we don't have the expanded, we have the extruded, but it was around 8.2 as well. Okay, so here it's 0.2, we can say 0.21 if we round up. So that would be 0.21. And finally, plywood. Do we have plywood here? plywood. Okay, I need this. So it's 0.9. I remember that it was 0.8 in the other table. I don't mind 0.9, 0.12. Difference. Let's type 0.9. And this is it. Well, remember that here we have a blank space, so we can drag this, and now we have the same formula. So this value is 31. I remember that we have calculated exactly the same detail with a different table, with different materials, and this value was not 31. It was, well, I don't remember, but it wasn't that number. It doesn't matter if it's 31, 32, 33. That's fine. We're close to 38. 38 is the minimum requirement for a passive house. From if we're above 40, we're good. So what can we do? I don't know. I would add a couple of inches of expanded polystyrene, and I'm above 40. So that's what I would do. Okay. So if the goal is to be between 40 and 50 for walls, 8 inches of expanded polystyrene might be enough. 10, it's better. With 10, we are above 50. But 8 might be enough. Okay, if you want to save a little money, let's go for 8. We are above 40. It's not bad. Well, it's quite good because we are above the passive house standards. But if you don't want to think and you just remember, oh, someone told me 10. Okay, so let's type 10 and you are on the safe side. So this is it. And that's the final sample. Okay, so you know what you have to do. We have 20 minutes ahead of us. Do this. Okay, so try to complete the assignment if you haven't done it yet. If you don't have a computer, if you do have a computer, do it. If you don't, you can go upstairs and try to go to the computer lab, or you can work with your classmates and you can do both. Okay, so or you can copy and paste, whatever. But I want to give you some time to complete the assignment now. And so please go ahead.